Hey everyone, this is Rohan. I'm one of the undergraduate tutors for MCBC100A, and today I'll be talking a little bit about ligand binding. So, in a previous video, I talked about how to relate free energy to equilibrium constants. I'd recommend you look at that. It's pretty relevant for what I'm going to talk about today. But today I'll dive in a little bit to how molecular phenomena affect how strongly a ligand binds to a protein, and then I'll talk a little bit about affinity and specificity of ligands binding to proteins. So to start off, the chemical reaction we're talking about with ligand binding protein is pretty simple. You have some small molecule ligand that binds to protein, and it forms a protein-ligand complex. If I were to write the equilibrium constant for this reaction, it's pretty straightforward as well. You have the complex concentration over the product of the protein concentration and the ligand concentration. Now, I wrote this reaction in a certain direction. I wrote it where I'm forming the complex, or the ligand is attaching to the protein. Therefore, this Ka, this K is an association constant, aka. I can relate this equilibrium constant to a delta G minus RT ln Ka. And because I wrote it in this direction, this delta G reflects the free energy of the forward reaction. In the forward reaction, we have ligand binding the protein, so this delta G is the free energy of ligand binding the protein. I can also write the reaction in the opposite direction. Instead of a Ka, I get a Kd, or dissociation equilibrium constant. And similarly, I get a delta G of unbinding minus RT ln Kd. And writing this all out kind of demonstrates that point I was making before, in how you always want to use delta G equals minus RT ln K. You always want to work from this definition. Don't take shortcuts. Don't try to relate binding to Kd. Always use this relationship and then do some algebraic manipulation to make it fit to the problem with the information you have. And very clearly you can see how you can relate Ka and Kd. Ka and Kd are reciprocals. So if I want to go from Kd to Ka, I do 1 over the Kd, and vice versa. And the free energy, I just change the sign. So delta G binding is just negative delta G unbinding. Pretty straightforward. The equilibrium constants for reactions in the opposite direction are reciprocals. And the free energy, same magnitude, but opposite sign. And once again, if you want a refresher on any of these concepts, I recommend you check out the video I made earlier that relates free energy to equilibrium constants. Now, it's important to get a understanding of the molecular phenomena involved with ligand binding. So you want to remember that when you have ligand binding with protein, the picture you want to think of is some small molecule and some protein with a cleft or an active site binding together. Just like how we could relate the equilibrium constant to the free energy, we can also relate the free energy of binding or unbinding to enthalpy and entropy terms. So if I wanted to talk about how strongly this ligand is binding to the protein, I should talk particularly about the entropy of ligand binding and the enthalpy of ligand binding. So we know that a spontaneous reaction, delta G is less than 0. So a spontaneous ligand binding event would mean that you have strong binding. So for strong binding, we want delta G less than 0. So ideally, we want a negative delta H. So for delta H, you want to think about what interactions are going on with the ligand and the protein. So obviously here you have free ligand, you have free protein, and when you form the complex, you form some kind of interaction. This ligand is not interacting with the protein active site. The stabilizing interaction, so you have one contribution from the protein ligand interaction. So there's some H protein ligand. And because it's a stabilizing interaction, we know this is less than 0. But you also want to remember that in order to form that interaction, you broke some other interactions. So for example, in solution, we don't just have a protein and a ligand. We also have water molecules. The water molecules are everywhere. And this interaction is competing with interaction with the water molecules. So the free ligand and the free protein both interact with surrounding water molecules. So the total delta H then is the protein ligand enthalpy, bond enthalpy, minus the enthalpy of the ligand and the water, and also minus the enthalpy of the protein and the water. So for this to be a strong interaction, for the ligand to really be strongly attracted to the protein, we need this bond enthalpy term, these interactions here, to be much stronger than the interactions here and here. So this enthalpy is the enthalpy of ligand-protein interaction relative to ligand-water interaction, protein-water interaction. Okay, so that's where the enthalpy terms come from. So for entropy, maybe at a first glance, you'd see that the entropy would decrease. You have some free ligand, some free protein, and they can translate anywhere they want in solution. And when they bind, they're stuck together as one unit. But actually, you want to look at the water molecules when you talk about entropy as well. When you have free ligand and free protein, the water molecules are locked into interactions. They're locked into their positions here and here. But when you have the ligand bind with the protein, these water molecules can more freely translate in solution. So you have an increase in entropy from binding by freeing the water molecules. Okay. So these two terms come together to define how strong of a ligand binding interaction you have. So if I wanted to modulate delta G, I could do that in several ways. First way very clearly is change the binding affinity, changing that binding interaction. So control protein ligand interaction. And I can also control the change in entropy, particularly of the water. Mostly from water. So, for example, if I made the ligand more hydrophobic, I'd really lock in, I'd really be decreasing the entropy in the free state. Great. So all those physical phenomena we just talked about control the affinity of a protein for a ligand. So if I want to talk about an affinity for a protein for a particular ligand, I can talk directly about the delta G. The delta G defines the protein ligand affinity. So a negative delta G binding, a very low negative delta G binding, much less than 0, implies high affinity. Okay, so that's protein ligand affinity. We also talk pretty frequently about affinity and specificity. So just to distinguish the points, affinity, like we just discussed, is directly related to the delta G binding. Delta G binding. And it's descriptive of one protein to one ligand. So, for example, I could give you a particular affinity that describes how hemoglobin or how oxygen binds to hemoglobin. Oxygen is a ligand, hemoglobin is a protein. However, that affinity doesn't tell you anything about something else attaching to the protein. And this is really important. Affinity refers to just one particular pair, one protein binding to one ligand. If I want to compare that to something else, I need to talk about specificity. So specificity compares two different ligands binding to a particular protein. So, in solution or in a cell or in some kind of biological context, you can have a common protein that has some cleft or some active site that binds to multiple ligands. So let's say one ligand is 1, the other ligand is 2. And both of these can interact. They can compete for the same active site. And you can have 1 binding to a protein and 2 binding to a protein. Very importantly, it is the same protein with 2 different ligands. And you can get association reactions for each ligand. So Ka1 and Ka2. If I want to talk about the affinity for the protein to ligand 1, I talk about Ka1 on its own. Likewise, I can talk about the affinity for protein to ligand 2 by Ka2. But now, let's say I wanted to say, how specifically does the protein select for ligand 1? And if I want to talk about specificity, I need to compare affinities. So something has high affinity if its delta G binding is less than 0, much less than 0, which implies that their Ka is greater than 1. This doesn't imply necessarily that that protein ligand is specific. For example, Ka1 could be much greater than 1. That doesn't tell me anything about how it selectively grabs 1 over 2. In order for me to say, so this just tells me about the protein's affinity for 1. For me to comment at all about specificity, I need to know how Ka1 compares to Ka2. So if Ka1 is much greater than Ka2, I know that this reaction is heavily dominated by forming the complex with ligand 1. And because this reaction dominates more, I can say that the protein is specific for ligand 1. So very importantly, affinity refers to one protein ligand pair. Specificity compares multiple competing pairs. The example I like to think about is hemoglobin. Hemoglobin can bind to carbon monoxide, it can bind to oxygen. There's two different affinities, and the affinities compete with each other. So I hope that cleared up some of the topics. If there's anything that's unclear, feel free to comment on this video or post on Piazza, and hopefully either me, their tutors, GSIs, or the professor can comment and help clear up the confusion. Thanks.